very expensive in the movies,
Like
in the
popcorn
cinema.
and drink.
Popcorn and
How
drink like €7.
Okay, it's not expensive.
I think that is.
€20 for one
Yeah,
set.
Is it the
Yeah,
same?
if it's,
Yeah.
They are expensive everywhere.
yes.
It's universal, it would seem. Yeah. Okay. Right. Let's have a look here at the next lesson. So this, oops, did I get this? Oh, I did. Oops. Okay. Right. So we spent a few classes looking at turning force, so now we're doing something new. If you can write this down. Work, yeah.
Okay, but we wrote this lesson. You finished it?
I did, yeah.
Written by
Yeah.
Ray and
Yeah. Okay, did you write this down?
Yes.
Okay. Work. Okay. By the way, what are you doing in chemistry at the moment?
We just finished crystal splitting.
So did
Transition method.
you do the mass spectrometer yet?
Yeah.
That was
the first topic.
Yeah,
we
we
did.
finished.
That was the first topic.
Yeah.
Oh, okay. Yeah, we'll actually talk a little bit about that as well. We'll look at more the physics of how it works later. I forgot about you. I was thinking, who's coming in here?
Hold it.
I'm so useless.
I wouldn't say useless.
Yeah.
Forgettable, maybe.
It's the same.
No, it's not the same. I know. Don't kill yourself, please. All right.
No, the way I remember those things.
Yeah.
You're
Not,
forgettable, but
not
you
final
forget.
destination. I'm not gonna fall or flip the table.
Yeah. And the cable gets wrapped. Yeah. Okay. Now, in this picture, work is being done. So, what things are needed for work to be done? If some work is being done, what do you need to see from like a physics point of view? So, yeah, if there's some work, then you think there's a force.
Yeah.
No, yeah, maybe there's a direction as well, that the force is in a direction. What else might you need to see?
Distance.
Yeah, there's some distance. Maybe you move this to here, so there's a distance.
Mass.
Maybe there's a mass as well. Yeah. So the ideas are, if there's work being done, there's a force. The man is shoveling, so there's a force. The force is making something move. So what is he moving here? The dirt, the sand, whatever. The sand. And there's a displacement. It's being moved in a direction here. The sand moves with the shovel. And the force is usually over an area. So like here, look, if this is the shovel, you have an area. So he's moving it like this. So you have an area, you have a force, you have a direction, and you have a distance. This is usually what you have. Now, you don't need to write this down. You don't need to write this down. I just want you thinking, okay? So, the two most important things is a force and that you move at a distance, okay? We'll look at this in more detail now. So, we say in physics, you do work by a force
Action on a body.
and it moves a distance. Now this is very, very technical, but as a simple formula, this is work.
But we need work.
Wait, no, I'll write it down. I'll show you here. So, as a formula, work equals force multiplied by distance.
It must be F into D. Always be written like F into D.
F or D, F, S, whatever. Yeah.
So last,
W is work, F is force,
Yeah.
and S is displacement.
maybe that's
Yeah, a lot of places use D as well. It doesn't matter. You can use D if you want. So work is F multiplied by distance. So if you can write this formula down, the formula is most important. I think the formula is enough, yeah. You should, Musharif, you should also write down what the W, the F, and the S represents.
So we need to write the definition.
The formula is enough.
Okay, I wrote the sum.
Yeah, but did you also write what the W, F, and S stand for?
Like I wrote work equals force multiplied.
Oh, you wrote it in as words. That's okay, yeah. Right, do we have this?
Yes.
So, what is the units? Or what are the units?
Newton meter.
Newton meters would be the units for work. The units used are joules. But a joule is just 1 Newton meter. It's the same thing. So 1 joule of work is when we have 1 Newton of force moves it 1 meter. So in other words, it's the same as saying 1 Newton meter.
Why don't you use meter?
You can, it's fine. So just to be clear, 1 Newton meter is the same as 1 joule. Now, please note, in the exam, I noticed that they like to ask this definition. They like to say, what is 1 joule? So the answer is, 1 joule is when 1 Newton of force moves an object 1 meter in the same direction as the force.
Can I write 1 Newton?
No, in the exam, they won't be happy if you just write 1 Newton meter. They want it as a sentence. So you can say, no, I'd rather you write it down. I'll give you the time to write it down. It's more important that you write it down. Okay?
1 Newton moving.
It's right there. 1 joule of work is when 1 Newton displaces an object by 1 meter in the same direction as the force. Okay? So look, let's say this is 1 Newton and this is 1 meter. Okay? This is 1 joule. If 1 Newton pushes for 1 meter,
We have a joule.
that is a joule of work. Yeah. Okay.
1 joule of work is when 1 Newton.
Yeah. And it's actually important that it moves in the direction of the force, okay? So here it moves horizontally and the force is horizontal as well. Well, just in my example. Okay. And again, I think I've seen them ask this question a few times recently. They like to ask, what is the definition of 1 joule? It's also, the other one they like to ask is for definition of 1 Newton. So 1 joule is 1 Newton meter, and also 1 Newton is 1 kilogram meter per second squared.
So when 1 kg of mass.
That's it, when 1 kg of mass, 1 Newton of force will accelerate 1 kg of mass by 1 meter per second
We
squared.
can define it in our own ways.
Exactly,
Yeah,
yes,
we know
yes.
If you know the formula.
If you know the formula, you can write the sentence. This is it. So if you remember 1 joule is 1 Newton meter, you can write the sentence. Okay, continue now. So, you don't have to write this down. This is just a question to do to get us thinking. Okay. So, I want to know, look, where and what is doing the work. Okay, so I want to know what is doing the work. First example, a mother lifting her baby up from the ground. So I want to know what is the force, what is the distance. The force, yeah, so the force is the lifting, and the distance, of course, is how high she lifts the baby. So this is the work. Yeah? You look confused. What's the question? Huh? Lifting. Give us another verb for lifting.
Picking up.
Picking up.
The way you pick the child.
Yes, like this. Okay. A woman pushing a large box along the ground.
Pushing.
So this is the force, and the distance?
The distance she's coming.
It's how far the box
The box.
moves. Yeah. A man kicking a football. Now, what's the force? The kicking in his foot.
Yeah.
Now, wait. Think carefully. What is the distance? Wait, no, stop. You said that way too fast. You didn't think about that enough, right? So think for a few seconds. What's the distance when you kick the football?
Legs.
Distance between the ball and the man.
No.
Isn't that the football?
No.
The second, the moment,
The foot.
Or the time.
touches the ball, it's really small.
You told us.
It's small, yeah. The distance in the example when he kicks the football, it only is the distance when his foot is touching the ball. So like if this is the ball here and he kicks it, you only count the movement when his foot is touching the ball. You don't count after that because there's no more force. He's not moving it. Do you understand that?
Yeah.
And then a child who hits the wall, what's the force?
Shoot the hit.
Is the hit. But what's the distance?
When he hits the wall.
0, 0, 0, because there was nothing in the
There is a reaction force that cancels it, but, I mean,
You think you know?
it absorbs.
we're getting close. So when I hit this, am I doing work?
No.
Yes.
Well, if I
There is
keep
force, but there is no
shh.
distance.
Listen. If I keep doing this, will I get tired?
No.
Yes.
Yes.
Yes. So I am doing work because I will get tired if I'm doing this. This is the force, but what's the distance?
Your hand and the wall
Is it like this? Like this is the distance.
Yes. That's it. So he has it. You can't, it's so small, but when you touch the wall, your hand
Oh
That's
my
it.
God.
flattens.
But this genius comes.
No, it's very small because the distance moves. Your hand flattens.
Yeah.
It can be neglected.
Well, it can be negligible, but if the force is big enough, then it's not because you multiply the force and the distance. So even though the distance is small, if the force is big enough, it still can be significant, you know. Yeah, so sometimes the distance is not clear. Yeah. And then the last one, now this one is very interesting. A father carrying his child. So maybe like the child is here. Yeah. What's the force?
There is no.
Yeah, like it's. Ask yourself this: will he get tired?
Yes.
Yeah.
Yes.
Yeah, he'll get tired. So he must be doing some work. But what is the force and what is the distance?
The force is his weight.
Not quite.
And the distance is the way he's moving because the child is also having the same distance as the father.
The far or
The distance maybe is like 1 meter, like his height.
Minus. Or
and the height of
The total height minus father's height.
something like
Yeah,
that.
like this.
Which part of him will get tired?
Shoulders.
Shoulders
Something
and
like this.
maybe legs as well.
Maybe.
the father will get tired.
Yeah, where? Shoulders and legs, yeah? So the force from the father to keep the child on him is up. So it's an up force. But then what's the distance? What's the distance?
The height of his leg plus the shoulder.
Yeah.
Just the shoulders.
But think about, like, if the father is moving, the height is changing.
Yeah.
So this is the distance.
The change of height while he's walking.
Yeah, because it's like every time he steps down, he has to lift the boy back up.
Yeah.
Can you picture that?
Yes.
Like as he walks, it's like he's doing an exercise like this. You have to keep lifting the boy up maybe like 4 centimeters each time. So he keeps doing this. It's like It's like this example, you know, keep repeating it. Yeah. Anyways, this isn't anything super important for the exam. It's just something that you really need to be thinking about carefully about force and distance. What exactly is the force and what exactly is the distance? Now the last one is actually interesting because when we look at this, we actually say that there's no work being done. Although in real life there is work being done. But in our examples, we assume that the father doesn't change his height. So he's kind of just moving along like this, okay? So if he doesn't change his height, then what's the distance? 0. So actually there's no work being done. But you know in real life there is one, okay? So the last one I think is kind of interesting. Right. Okay, so what we'll do is we'll do an example here. You can write or draw it. So if you can write or draw this, and I'll do it. Okay, so this is our first example. Yeah, the first part is that, yeah. So let's draw this. If we read it, it's 100 kilograms. So here's the box. 100 kg. A woman pushes the box. And the block starts at rest and reaches 1 meter per second over 5 seconds. So here it's at rest. Then she pushes with a force and it moves. And then here, 5 seconds later, it's moving at 1 meter per second. So did she do some work?
Yeah.
Definitely. She pushed it. So the first question, I want you to do this. What was the acceleration? So part A, what's the acceleration? I want you to calculate that.
Could you please show me that?
It's a beautiful diagram.
What is that?
That's the first question, yeah.
What is that?
Oh, you missed this lesson, so you have to watch this video. What lesson did we do acceleration in?
In the
Equations of motion.
yeah.
Yeah. So you just have to wait to see how I do this one now in a moment.
Can we see the question?
What is fine?
Ooh, I'm glad it's nearly lunchtime.
Acceleration, okay. So
I have the answer, but I don't know it's correct or not.
Let's do it. U, V, A, T, S. What's the U?
0.
V,
1.
A,
No.
don't know. T,
5.
5, S,
No.
don't know. Which equation?
V equals U plus 18.
V equals U plus AT. 1 equals 0 plus A 5. 1 equals 5A. A equals 0.2 meters per second squared. Part B. What is the distance? Part B, give me the distance.
What was the
Distance.
Literally,
Ham, what's the question?
what is the age?
Yeah, it's not 0. We want S now.
2.5.
Let's calculate, yeah. So what formula did you use, Iad?
S equals U plus
S equals UT plus a half AT squared, which equals 0 plus a half 0.25 squared. which equals 2.5 meters. Okay, great. Is that okay? Part C. What was the force? So part C, I want you all to tell me the force here. What's the F?
20.
Yeah, how'd you get that? What do we use?
F equals
F equals
ma.
ma equals 100 times 0.2, which equals 20 newtons. D. What was the work? So yeah, what's the formula for work? Force multiplied distance, 20 times 2.5 is 50?
2.5.
50?
50, yeah.
50 joules. Yeah? Okay. And then I think there's one more part. If she has the same force, okay, the same force but on an angle of 10 degrees to the horizontal, then how much work was done to the block? Now, please, before you write anything, look at me and listen carefully, okay? English time. Listen carefully to my English, okay? So, we can use work two ways. I can do work, or I can do work to something. For example, if I just do this, I'm doing work, okay? Or we can say work is being done to the cup. Now, imagine I have two things, okay? I'm doing this. So I am doing work. Or we can say work is being done to this, and work is being done to this. So in this question, I said how much work was done to the block, not how much work
Was done by.
by the woman. Now that difference is important. Let me show you why. Here is the block. Here is the woman, and she now pushes at an angle. This has two forces. If you are the block, which force do you care about if you're the block?
Horizontal.
The horizontal, because this makes you move. If you are the woman, which force do you care about? No.
The reaction?
She cares about this one because this is what she's doing. This one here. So this is the one that she does, that she cares about, for the woman. Do you understand? So if I say the work done to the block only cares about this one because this makes it move. It doesn't care about this one. And it doesn't care about this one. Why doesn't it care about this one? Because it doesn't make it move. It's only this one that makes it move. Does the woman care about this and this? Yeah, because she has to do it. So she feels it.
Yeah.
This one and this one she feels. So that's very important that I said work done to the block. Or the work by the block or whatever. Okay. So, in our calculation, what was the force? What was it? 20 newtons. We don't care about this if you're the block. You only care about this one. 20 cos 10. Okay, so what's that, please? This is for part E.
19.6.
19.7 newtons. Yeah. So what is the work now? It's 19.7 multiply 2.5.
49.3
49.3,
joules.
joules. Yeah. So, do you remember in my definition I said you only care about the force in the direction of the movement. You don't care about the other direction, just in the movement. You understand what I mean by this? So if I push this, I only care about this force, not this force. Okay. Right.
Can we see the question?
A few seconds. But I need to move on. We haven't got too much to do. Okay. Continue. Yep. And then, right. So, there is another element at play. So tell me this, why does standing on one foot feel more difficult?
So we can't balance the mouse.
No, but why does it feel harder on your foot if you have one instead of
The
two?
body is now only on one.
So
Yeah, if you think about this. 2 feet, we have W, and we have R, and they're equal, and then 1 foot,
What is double?
wait, W is the same, R is the same, but this feels harder, and it's because it's one, what's the reason? No? The reason is
the balance.
All the art is on
less area. So here you have this and this. Here you have just the one. Okay, so there's what you might say there's more force per or more technically per area, but you're right, per leg. Yeah. Your weight is the same, but so the example is with the ballerina. Okay, now the ballerina is even more difficult because she stands on her toe, which makes it even harder because it's a smaller area. And I don't know, you can Google the pictures of ballerinas' toes, but they look really bad. Yes, because it's very difficult to do this on one toe. If you can imagine all your weight on a small area, it's quite difficult.
The leg will be broken.
Toes do break. The toes do break. So this gives us the idea of pressure. Have you heard this word in English? Pressure? Yeah, pressure is
Force per area.
Something stress.
like this, yeah. This here, if I do, let's see, if I do this, that's more pressure than this. Yeah, this has big area, this has small area. So this has more pressure, less pressure than less pressure. Yeah. And this has big pressure. Yeah. As a formula, maybe you know what pressure is. It's force divided by area. This is pressure. What's the units?
Force per area. It's Pascal, I think.
Yeah, but if we just looked at the formula, what's the Newton per meter squared? Yeah. Okay, so the formula is enough. Formula. Yeah. Now, you said it, Mir and Iyad, the units would be newtons per meter squared. But often we use a unit called Pascal, and we say 1 Pascal of pressure is 1 Newton for 1 meter squared. So, if I just draw that for you before you can continue. This here is 1 meter squared, and this here is 1 Newton. So we say the pressure is 1 Newton per meter squared, or we call that 1 Pascal. You look so confused. What's confusing you? Yes? Yeah, so you missed this. Did you watch any physics videos?
Yeah.
Did you watch the first videos?
Yeah.
Are you sure?
Yeah.
Okay. Units and dimension. Yeah? So, recap quickly. If I say A per B, that equals A slash B. But we write it like this. So, for example, meters per second is meters slash S, but we write ms minus 1. So, if I have here 1 Newton per meter squared, that's 1 Newton slash meter squared,
Newton
1 Newton m minus 2. Oh, you look so unhappy.
Can you like show?
No, 90 degrees.
No, I mean like 1 Newton over.
Yeah, okay. You could also say 1 Newton like this. Yeah, okay.
Yeah.
Yeah.
Go on.
It's okay? Are you sure? Do we believe you? Yes? It's okay? Sure? Okay, fine. Well, we'll continue. If it's not okay, let me know. Right. So, again, this is something they also like to ask. What is a Pascal? A Pascal is 1 Newton of force on an area of 1 meter squared. They like this one in the exam as well.
Because I write this 1 Pascal of pressure.
Is 1 Newton of force on 1 meter squared of area, basically. You just write this down.
Only this, no?
Yeah,
Not all this.
but safer to write this. Just to be safe. Yeah. Yeah. Okay, you have this? Yeah. So we'll have a look at an example with pressure now. And then I think that will be it. Let's have a look. So 1 Pascal is the same as 1 Newton per meter squared, like I said earlier. I think you should also just add that. You can just write it like this. This is the same. Okay. Continue. Right. So you don't have to write this down. This is the same as the example earlier with the woman. It's 100 kilogram box. It's the same story, isn't it? The only thing now is, I say, her hands are each 100 centimeters squared, her hands, the area. What is the pressure in her hands? I want you to do it, then I'll do it. What's the formula for pressure? F over A. Do you know F?
Force.
Yeah, you have it from the last one.
Oh,
This is the same. This is the same.
Okay.
Yeah. Do you know the area?
10.
There it is there. Okay, calculate.
X upon 20 upon 10. 2.
200.
2.
200 what?
100 centimeters squared, I change it to meter. Is that?
Yes, correct.
So
You
it's
should
not-
change it. I won't tell you until I do it.
Here's the this is
Okay, when we multiply.
Correct, he's right.
who's that? You.
You are. Look, her hands are each 100.
Okay.
2
So 200 then.
It should be 200. So I'm confused always in this conversion of units. When it's meter squared, so it's now
I'll do it
centimeter
now,
squared.
I'll
No,
do
no,
it.
I'm just asking the conversion.
No answer. So sorry. I'll show you instead. Okay, let's look at this. So this is our example then. So pressure equals force over area. What was the force? I don't remember. 20 newtons. I'll write newtons in here.
Okay, but when to, from where we go?
This was the last example. Yeah.
Okay.
Now, she has 2 hands, not 1, 2. So it's 2 multiply 100 cm squared.
So we will transfer the.
We have to, yes, yeah. So this is 20 over 200 Newton over cm squared. What's 20 over 200? That's 0. No, 1. 0.1. Newton over cm squared, actually. Now, wake you up time. How big is a centi? No. See, you're forgetting everything you did in the first lesson. Centi.
0.0.
0.01
Yeah.
meter squared.
Yeah.
So this will be 0.1 Newton over 0.0001 meter squared. This here, I square.
1,000.
I square. Square.
1,000.
What? So you got 1,000?
Yeah.
So this is 1,000 Newton over meter squared. What did we say this is? Pascal. This is 1,000 pascals. What's 1,000?
1 kg.
Try again. 1 K.
1 kilo.
1 kilo Pascal is the answer. Now, no wait, listen. I put this question in because I wanted to test to see if you remembered what we did in the first lesson. And I don't think I heard anyone say 1,000 as the answer. Well, you're off by a factor of 10.
Yeah.
Yes? So what we're doing here is stuff from the first lesson. From here,
I understand.
yeah, this is from the first lesson. This is from today's lesson. I can go back to the question.
Yes, please, yes.
Yeah.
I just want to check.
Trying to check something. Okay. What do you need to check?
Couldn't I just change the 100 centimeters squared before I get
Yeah.
to the final?
Yeah, you could. You could. So
Easier.
if we change it like this, 100 centimeters squared equals 100 centimeters squared equals 0.01 meter squared equals 0.0001 meter.
This is 100. Not the.
0.0001 meter squared. 0.01 meter squared. Yeah. Did I get that right? 1, 2. Yes.
I think we only have 2.
You can do that. Yeah, that's fine. And so then pressure equals, what was the force? 20, and the area is 0.02. 2 hands. So this is 1,000. So yeah, if you want to convert it before you do anything, perfectly fine. It would look like this. If you want to convert it later, which for some reason I prefer, I don't know why, it would look like this. And maybe this is a bit messy. So if you want to write it like this, actually that might be better. Yeah? Okay. So this is another way to write it. Yes?
Yes.
Yeah. See? Revision, important. Yeah. Okay, can I continue?
Yeah.
Well, look, if you didn't write this down, you have to get it from the video because we're running a bit late. So, again, 4 questions here to do. So what have we got? Monday, isn't it? Yeah. So let me just check how we're doing for progress. What lesson will we be on? How many? We have 2 weeks left, yeah? 1, 2, 3, 4, 5, 6, 7. Yeah, we should be okay. I need to get to this lesson before the break. Okay? Because if we don't get to this lesson before the break, we are behind schedule. Okay, so we need to get here before the break.
The October break.
Or
The midterm break, yeah. Yeah, because your midterm test will be on all of this chapter, mechanics. Okay. Alright, if you want to take a picture of this, you can. I'm going to close it down in a sec. It's also on Moodle. You take a picture too?
Yeah, but
Why not? Everybody else is. He's doing it the Moodle way. Yeah, which I don't know why people, like, I mean, I've uploaded the nice clean PDF onto Moodle.
Yeah.
I don't know why you would want to look at a blurry picture to...
I always use
Easy.
the Moodle.
Alright, okay.
I always use Moodle.
That's the only reason, really.
I also give you likes and views and stuff.
Yeah, I like the likes and views. Yeah, I'm at now 104 subscribers.
People watch your math more.
Yes, well, there's more people doing it.
Exactly.
Okay, pause this.